let's look at, we looked at DBX, we looked at runtime memory checking. Let's look at something called as advanced profiling here. What I'll do is, I'll set the profiling interval to high, and I'll select clock-based profiling. We'll come to what this is in a while. I'll just close this, and I'll say advanced profiling, and I'll say start. Yeah. So again, let me just play the game for a while. See if we can collect data. I'll say quit. So it generates something called as test1. It gives me a whole bunch of tabs, and it gives me a few columns where it shows me function names, the names of functions, and it gives me something called as user CPU second. Okay, let me just add another column to this. I'll call it as the total thread. Okay. So let me just sort this, and if you look at this, we ran the program for about 22 seconds. For about 22 seconds of human time. Okay, and here, this is an interesting little bit tidbit. This is an interesting piece of information. It says user CPU 0.124. That means this piece of code, this program, was on the CPU, was executing on the CPU for about 0.124 seconds. Okay. Obviously this is an operating system, and there's a whole bunch of other processes running as well. So there are context switches and so on and so forth. But this particular program, the Tetris program, got about 0.124 seconds on the CPU, of CPU time. Interestingly, there's something else called as the timeline as well. What we can see here is we can see certain call stacks. Just give me a second. Yeah. So this is the timeline of the program throughout. This is about 22 seconds. If you look at the whole graph, it's 1 to 22. That's the whole timeline of the programs, and you can see what the program was doing from 0th to the 22nd second, right? So here you can click on one of these, and here to the right side it will show you that this was the call stack, right? It was doing an ioctl call here, and this here it was nano, it had called nano sleep. You can see that the stack throughout the program is fairly similar. So the program is doing something. You need to know what is it really doing over that 0.124 seconds. Let's look at what it's doing. So what I can do is I can go to main, and I can go to the source. If you notice, look at my mouse pointer here. If you notice, there's a very small green line that's shown here, right? There's a very small green line. If I click that takes me to something called as a hotspot. So out of 0.126 seconds that we have here, 124 seconds that we have here, most of the 0.12, out of 0.124, we were sleeping for 0.121 seconds, right? So that's where most of the CPU time is being consumed. So now if you have a program that you think is performing slow, you could run it through something like the profiler and see and check for hotspots. It will actually show you, different time, different functions where you've spent the most amount of time. Make sense? How many of you have used such tools before? How many of you would want to use such tools before? For now, when I was a student, I used to write programs in GCC and so on. Such tools would really help, for you to understand what happens in the system. So you have a timeline, you get a timeline, you know what your program is doing. Over the timeline, you can see what functions are being called, what are not being called, so on and so forth. So this is the performance analyzer. So we'll come back again to yet another demo. I have something called as the thread analyzer. how many of us have heard of race conditions and deadlocks here? We all study about race conditions and deadlocks in our college. We look at how some of the tools that ship with Solaris Studio actually help us identify what a race condition is and where a race condition or a deadlock exists in our code, right? We look at that demo. So I have a small program here. I've already built it using Sun Studio, but the code is very simple. The code is just this much. Visible? Okay. So this is actually an OpenMP program. Unlike pthreads, we actually have different constructs by OpenMP, such as OMP parallel. You can actually define regions where you can say that this block of code is actually going to be multi-threaded, right? So you can say that hash pragma OMP parallel will actually say that this block of code is multi-threaded, and you can also specify shared variables using the shared keyword. You can say shared of n, which means to say that n would be a shared variable if multiple threads run over them. So here we have a small assignment. We have a printf within an OMP single block, which means to say that it would be executed only once, regardless of how many threads run through it. And we have an n equal to OMP get thread num, which would say what thread number it is, and we print the thread number, right? There's a problem with this code. What do you think that is? Anybody can you guess any problems with this code? Sorry? N is shared, there's a deadlock? No. Shared variable being used in different? Used in different threads. In multiple threads. Okay, that's quite close. But let me just show you something. I'll say make demo. It runs the program and it brings up something called as the studio analyzer. Obviously my makefile has commands to bring up the thread analyzer as such. Here it says there's something called as a race in line number 22, right? Here it shows that if you look at the number of, I just clicked on dual source, and it says that there is actually a race condition in this particular line, which means to say that there are actually multiple threads trying to write to n at the same time. Okay, get it? So the outcome of the value of n could be different depending on which thread actually wrote first. So threads actually try to race each other. That's a race condition, right? So if you actually have you could also have a deadlock where you could have one resource, holding a lock, a thread holding a lock, and it's trying to grab another lock, whereas another thread is waiting on this which holds it. So you can have a circular deadlock and so on and so forth. So such conditions can actually be detected by the studio analyzer. So it does analysis depending on what code, depending on the binary that you give, and it does runtime analysis and points out that there's actually a race condition in your code. So this is one small demo of a studio, of a race condition. Here you can say that you can see that the type of the race condition was actually right, which means to say that n was being written into, and it was more of a write data race, if there's such a term. So that was one demo. We'll now move on to yet another feature called dlight. I have a separate program for that. So Solaris provides dtrace. How many of you, was there a dtrace talk before this one? How many of you know what dtrace is?
It's coming up after this one.
It's coming up after this one. Oh, right. So Solaris provides something called as dtrace, which allows you to instrument your code, which allows you to instrument your system, your operating system, as well as the code that you write and the applications on top that run on top of the operating system. When I say instrument, it lets you, see what function calls are making. It lets you collect some amount of times, between holding locks, releasing locks. It lets you tell you how much time it took for an IO to happen, so on and so forth. So dtrace lets you instrument, and maybe you should attend the dtrace demo because it's really one of the most revolutionary products that have come out in the recent ages, especially in the Linux world. No other operating system has dtrace. So this particular demo is more of a delight demo, which uses the dtrace functionality which is available on Solaris to profile this application. So I have a sample application. This application, what it does is it can do two kinds of work. It does work one, which does some amount of mathematical calculation. We're not bothered about what mathematical calculation it can do, but it does some amount of mathematical calculation. And the second work it does is it writes into a file. Okay, so we look at some amount of behavior. We look at how this program behaves, depending on based on what delight tells us. Delight will help us figure out how the application behaves. So this is called a profiling demo. I'll just set it as the main project, and I'll say delight main project. Okay, so we have a few instruments here on the left hand side. One of them is the clock profiler. We'd be using something called as the microstate accounting monitor, so I'll just double click that, use that. I'll use something called as the heap monitor. I'll use something called as the clock profiler. So we look at what each of these instruments do in a while. So of course, let's not dig into the source, because the point is we'd want to understand what the program does by looking at what dtrace gives us or what delight gives us. So I'll start this program, and here in the output window it says this is a sequential demo. This part, the one that I'm just highlighting right now, not the graph. It says sequential demo. I'm going to run two works sequentially, and we'll start off two sequential works. It's not a multi-threaded program until now, but let's start off some amount of work. Here we can see that there are two graphs that are coming in, and here it says press enter to start this work. So if I click on this graph that we have here, it says, it shows, yep, yeah, sorry. Yeah, so here if you look at this particular graph, the blue and the pink bar that are running across the screen, I'll click on the microstate accounting monitor, and here it gives me a number called 1000, which says asleep on condition variable, which could probably mean waiting for IO to happen, which is what we're doing here. I'll say enter to start this work, and now what happens is we can see that the graph changes. Okay, we look at what these graphs mean in a while. So what it did is, if you look at the output here, it said work 0 start writing temporary file, and work 1 loads 1. We still have to start off work 1. We just started off work 0. We'll start off work 1. This is doing quite a lot of calculations with about 10,000 bytes of memory, right? So we see more graphs. Here below again, you can see more graphs here. We'll just come to that. Let me just run through the program and we'll come to that. So here, once we ran two sequential demos now. One was we wrote into a temporary file. Second stage, we did some amount of mathematical calculations. We'll now run these two demos in parallel. Okay, so the whole program, the C program that's there here, is actually programmed to do this. As in, this is just the same program which now does both the works using two threads. Okay, which is of course using pthread create. We'll be doing the same thing with using two threads. I just hit enter again. What you can see is you have more changes to the graph. You have more things coming up. Right? So what we see here in this case was these two works being done parallelly, by two different threads. Now what we'll do is we'll make one of these threads hold a mutex, or hold a lock, and then the other thread which is supposed to do the other work should also hold this lock. So only one person can hold the lock, which means to say that only one of them can run. And when one thread releases the mutex, the other gets to hold it, and then that does the work. So it kind of switches between both of them. Okay, so I'll hit enter again, and we get more colors. We look at what these colors mean, but we got more colors. Great. So that kind of completed our demo, but we still haven't understood what the colors mean. So okay, let me say fit to screen. So this will give me the entire program timeline, right? This gives me the entire program timeline. We know from our first bit of explanation where if I click on this particular timeline, it gives me some info. If I click on this particular timeline, it gives me more info here. Look at the dlight event details window. It gives me more info, gives me some more info. So for different things, it gives me different info. We look at each stage of the program, we'll see how we can figure out what the program does by looking at what dlight tells us. So we know here that I was about to hit enter, right? We were waiting for IO to happen, it was still waiting for my input to hit enter, which is what this says, right? And then we moved on to the sequential demo where what we did was we actually started writing to a temporary file, didn't we? Right? So here if you look at the data that's presented here, it says 925 and it says 74. Okay? So there was only one thread running, and if you there's more of a ratio. It's 925:74 or something like that. It's more of a ratio where it says that most of the time was actually spent in doing a system call, right? It says running in syscall or page fault. So most of the time was actually spent in doing a system call, and some of the time was actually spent in running the program in user mode, which means the program code itself was being executed if it wasn't doing a system call. Okay, so that was one part of it, right? So we look at this particular stat here, which was more of mathematical calculations, wasn't it? So mathematical calculations as such, what was the system call? In the previous example here, this one, what do you think was the system call? It's an IO operation, which is a write operations, right? So here in this case, it's not a mathematical, it's a mathematical calculation, and it's not a system call, which means it's running in user mode most of the time, right? Let's look at more info here. We then move on to the parallel demo. We're doing mathematical calculations and we're doing writes at the same time. Oh, sorry. So let me just zoom in a bit, right? So this zooming in gives me more info. So one thread here, we now have 3 threads on the machine, on the program. One is your main thread, which spawns 2 other threads. The 2 other threads actually do most of the work, don't they? So one thread is waiting, asleep for some other reason, and one thread is running in user mode, which is 950 here. The other one is doing system calls, right? So we have more latency introduced because of 2 threads, which you can see waiting for CPU here, right? So that's mostly the behavior that you see. Now, if you want to look at the call stack, we also saw a similar call stack in the performance, in the performance analyzer earlier, right? So here you can see that the call stack shows a write system call being made. If you look at this is fwrite, okay. So this is mostly again, that was thread 1. So we actually have multiple threads here. We have 2 threads. This was thread 1, this is thread 2. What is thread 2 doing? Thread 2 is calling a function called work run within the program, which is why we see it as running in the user mode at all times. Let's move forward. So this is where it holds a mutex and each of them run exclusively, right? here if you come down, you can see the interleaved accesses. This particular thread is doing write, and once this releases the mutex, and then this takes on. Then this releases the mutex, this takes on. So on and so forth. So you can actually observe how your multi-threaded apps behave with dlight. So there's another interesting tidbit of information which you can see with the heap monitor. Let me just set a couple of options here. It's called logarithm and let's say overlay, right? Yep, so this is where we were doing the mathematical calculations, and we were using about 10,000 bytes of memory to actually do this calculation, right? So interestingly, if you actually zoom in and look at the last piece of data that you have here, you can see that this was where the mathematical calculations were happening. So you're using 10,000 bytes, around 10,000 bytes, and this was where you were doing your writes. Here you're using 10,000 bytes again. Oops, sorry. Yep, this is where you're using 10,000 bytes again. You're not using, you're using a lot more. So you can actually observe the difference in behavior based on your heap monitor as well. So you can see that you use so much memory depending on what stage you're running at. So that would be it. So these are the kind of tools that we have that ship with Sun Studio. DBX, the thread analyzer, all of these can run as standalone applications as well. So if you're a Vim or an Emacs user and you don't want to use the IDE, if you're an IDE hater, probably you could use them as standalone tools as well. So we looked at all of this: performance analyzer and thread analyzer, dlight, debugger. So those are the 4 P's. One was performance. We can use tools such as dlight, the performance analyzer. Parallelism, we looked at autopar and the expector. This one, productivity. You can use DBX. You can debug your applications much faster. Platforms, Sun Studio and the compiler suite lets you use you can run them on Solaris or Linux. All platforms optimized for all Intel, AMD as well as Spark platforms. So that would be it. Where do you download Oracle Solaris Studio? You need to go to developers.sun.com/sunstudio, and there's also go to search.oracle.com and search for Oracle Solaris Studio. That's where you can actually get them. If you have Open Solaris installed, you could also just download it via the IPS repository. You can just do a pkg install Sun Studio 12u1, I think so. Yeah, that would be it. So if you have any questions, we can take them now, or if you have any detailed questions, we could take them offline. I have 45 seconds remaining though.
Can
Sorry?
I get Sun Studio on OpenSUSE?
Can you get Sun Studio on OpenSUSE? Yes, I think you can. Yeah.
Check the package.
You will have to go to developers.sunstudio.com.
Okay.
Download the tarball. You'll have to download the tarball. Yeah. Sure. Okay. Yeah.
For CPU affinity, let's say you said
CPU affinity?
Yeah, setting a core affinity for a thread.
Okay.
Thread or any of those.
Okay.
I do understand there are APIs available for setting the core affinity.
Okay.
But how do you, or basically there might be some algorithm you're using when you provide a compiler option for automatic parallelism, which you demonstrated a while back.
Right.
But as a programmer, when I want full control, let's say I have 4 threads and I want to run one of the threads in so-called one of the available cores.
Right.
I'll be exercising these affinity methods. But how do I know at any given point how loaded a core is? So what is the architecture behind that?
How loaded a core is?
Yeah.
Okay, so this your question, as I understand, it's actually not related to autopar at all.
No, see, I'll correlate it. Now
Okay.
you showed me an example where you had probably 2 or 3 threads running and you ran on auto, some option you gave, and it was switching between different core based on some algorithm or some scheduling algorithm.
Right, that the OS does it.
OS does it,
Right.
precisely.
Right.
Now, let's say I don't want that. I want one of my threads to run in 4th core
Okay,
specifically.
okay.
That can be done using, I think, set core affinity or some APIs are there in the library.
Okay, I'm not aware of those.
Okay, so my question is based on that. Now, I know how to set it on a given core using your Solaris OS,
Okay.
but I don't know whether that's the right core to set.
Okay,
So how do I know that?
so I think
Because-
if you want to look at the load that is on a particular core at a given point of time, there are again, you have CPU stat and so on and so forth, which you could monitor what your cores, how loaded your cores are, how loaded your CPUs are.
Are
So
those
at-
system APIs or are you talking about a shell command?
They are again tools which some of these tools actually use dtrace to tell you.
No, hold on.
Okay.
Not on tools. Not on tools. I'm
Okay.
still in a C program or C++ program
Okay.
probably. So where do I get that from?
So using a C program, you want to look at how loaded your cores are.
Yeah, there are APIs to set it to a core, but how do I know if I'm setting it to core, I'm increasing the productivity or decreasing it?
Okay. So,
MP stat.
okay. Do you have more info about MP stat?
No, it shows about for every process.
See, those are
No, but those are again
system
tools.
commands. Netstat, MPstat, all are system commands.
Right.
But you are having overhead running those commands again using system call or so-called.
So you need a
Yeah.
programmatic way of
Yes,
doing it.
programmatic. That's precisely what your compiler is doing when you say in autopilot mode.
So when you do auto par,
Yeah, whatever.
it just creates so many number of threads, depending on what environment variable
And
you
then
have.
those threads, based on certain algorithm, he's putting on certain core.
So that the OS does it. Autopar doesn't do it.
Yes, that intelligence, when there are methods available in Solaris to set it to a certain core,
Right.
why is there no other API supported to know the load of it? How will it sounds like it's incomplete.
So no, what I do understand is, it's the job of, the OS to, to determine what core you want, what thread should go where.
That would have made sense if there was no methods to set
Okay.
the affinity.
Okay, I think we are 3 minutes. What we'll do is we'll discuss this. We'll take this offline. We'll take this off.
Sure, I do appreciate. Thanks.
Do we have any more questions, or what we'll do is we'll take it offline. We're running behind time, so I think we can take it offline. I'll be here.
You want to take the question or?
We'll take it offline right
Yeah,
after.
sure.
Right. Great. Okay, so if any show of hands for more questions, I'll be here for a lot for more time. So, okay, just 1, 2, 3 questions. Okay, great. Thank you. I hope you enjoyed.